welcome to the IRENA online seminar. This is the first seminar of the semester, and we are going to take an opportunity to welcome the new organizing committee. My name is Ana Becerril, and I am at Michigan State University. I am the managing director of IRENA, and our IRENA director would like to address you all just today to introduce the new committee. And that's Henrik Schatz, and he is connected.
So welcome everybody to the IRENA seminar series. I'm very excited to kick off the fall series. This has been going on for many years, and I think it's a very successful activity. In case you don't know what IRENA is, I thought I'd throw up the slide really quick. So IRENA is the International Research Network for Nuclear Astrophysics. It's a NSF XLNet network of networks. So the idea is to network together various nuclear astrophysics networks across the world to foster international connections, exchange, collaboration, which, as you probably all know, are extremely important for nuclear astrophysics. And so these are the participating networks. You may know that the NSF funding for IRENA runs out in 2 weeks. So we're still going strong, but we had a lot of discussions with the various network leaders, and everybody's committed to continue this framework. We'll just have to use some of the local funding that's available in the individual networks. But IRENA will continue, and the seminar series is one of the elements that will definitely continue. This series is entirely organized by a group of students and postdocs from various participating networks. And so I'm really excited to introduce the new committee for 2025-2026. The chair is Stefan Türkat from Dresden. And I guess I'll read through the other members. Bobalak Sey from Hungary, Arakeli Garcia Flores from Mexico, Aldana Kriechner from ASU, sorry about my German accent, Sota Kimura from University of Tsukuba in Japan, Linda Lombardo from Trieste, Kang Pham from Texas A&M, Roberti from the Chennai Mathematical Institute for the LIGO collaboration, and Artemis Santieri from Regina in Canada. Thank you so much all for volunteering for this. I think we have, again, an amazing committee and a very exciting program coming up. We're very grateful for you guys to do this. We hope that this is also a good opportunity for you to network, networking with the speakers and networking with each other. If there's anybody in the audience who's interested maybe in doing this, there will be a new committee a year from now, and you can contact your network if you're interested in being on the committee the next time. But okay, so for now, we're kicking off the fall series, and we're looking forward to an exciting talk today and exciting talks in the upcoming series. And I hand it back to whoever's going to lead the introduction today.
That will be me, Henrik. Thank you very much for the introduction. Hi, everybody. Thank you so much for being here. I am Artemis Santieri. I am a postdoc at the University of Regina in Canada. I am so happy to host this first IRENA seminar for this year. As Henrik introduced, we are 9 postdocs from the 9 different networks of IRENA, and we will have great seminars every 2 weeks. Our first speaker of the season is Lorenzo Roberti. Lorenzo is a postdoctoral researcher at INFN, Laboratorio Nazionale del Sud in Catania. His main work is interest in the evolution, final state, nucleosynthesis of massive stars at different metallicity and with different initial rotation velocities. And he's currently working on the theoretical modeling for the Pandora project. The talk will be 40 to 45 minutes. It will be recorded so we can post it later on YouTube. And any questions, if you can keep it for the end of the talk, that would be appreciated. I will be monitoring the chat. Lorenzo, you can share your screen and start whenever you're ready.
Okay, can you see my screen? Can you hear me?
Yes, thank you.
Perfect. Okay, thank you for the introduction and thank you for inviting me here today. I am Lorenzo Roberti. I am working in Catania as a postdoc. I'm part of the Pandora collaboration, but also I'm very interested in nuclear astrophysics, and I'm still part of different ongoing collaboration with the Budapest group, with the Rome group, and also part of the NuGrid collaboration. So the thing I would like to discuss with you today is something that is happening toward the end of the evolution of massive stars that so far has been my main interest in studying. So just for those of you that are not familiar with evolution of massive stars, this is a very simple cartoon on how we expect the structure of the star before the collapse of the iron core, so before the core collapse supernova phase of the star, so before the supernova. So the star has ion core that is about to collapse under its own gravity because there are no nuclear reactions that are able to provide energy to counterbalance this gravitational pressure. And this ion core is surrounded by different layers of different chemical composition that we call burning shells, in which lighter nuclei are converted into heavier ones. Like, for instance, there is the silicon shell that is converting silicon into ion peak elements, and the oxygen shell, where oxygen is converted into silicon and sulfur, then neon, carbon, helium shell, and if any, the hydrogen shell and the hydrogen envelope. So in these zones that we call shells, the fuel is converted into a convective environment. So basically, at the bottom of this zone, there is the actual conversion. So there is the peak of temperature where the elements are converted into the heavier ones. And then turbulent motions can mix out this product of the burning, but at the same time can mix in some fresh fuel. So basically, in the entire zone, the fuel is consumed uniformly. This is working in most of the shells. So what's happening in what has been found in the last 25 years or so in 1D modeling of massive stars with an initial mass lower than 25 solar masses is that the oxygen shell, when it forms before the core collapse, so few days before the core collapse, let's say 1-2 days before the core collapse, can start burning oxygen very intensely, and its external border is advancing in mass, ingesting more and more material. What can happen at some point is that the external border can start ingesting not only fresh oxygen, but also material from the surrounding shells, like neon and carbon. So this transport of lighter species, or species that burn at much lower temperature at the base of the oxygen shell, trigger the so-called convective reactive event, in the sense that they produce a burst of energy because they are instantaneously burned, and in turn the external border of the convective shell advances in mass and in radius, ingesting more and more material. So at the end of the day, basically the net impact is the formation of a single mixed zone characterized by a very extended radius and very extended in mass as well, let's say between 1.5 solar masses wide, that is also characterized by a very peculiar nucleosynthesis. It's also interesting because it can change the density profile before the collapse, and then therefore can also impact somehow the explodability and the final fate of this star, so the final fate of the core collapse. And the interesting part is that this phenomenon has been also studied in 3D, and very recently I would like to mention the work by Federico Rizzuti, in which they also demonstrated, simulating a portion of the star in 3 dimensions, that the entrainment of material from the outer edge of the convective shell is a natural phenomenon. So it's something that is apparently occurring also in nature, it's not only a feature of 1D model. So, well, what I would like to discuss today is basically the second part of this paper that has been recently published in Astronomy Astrophysics. So if you're interested in the topic and if you're interested in this carbon-oxygen shell merger from different set of models, please check the paper out. This is the QR code, and I can share the presentation with you. This is the link also to the paper. So in particular, what I would like to focus on is the nucleosynthesis part. The nucleosynthesis part related to this merger between different shells. I would like to classify the nucleosynthesis impact in two different categories. So the first one is basically related to intermediate elements. So I told you that all this mechanism is generated by the advancement of the oxygen shell. So basically, we can consider the carbon-oxygen shell merger as a giant oxygen shell. So that is governed by the temperature at the bottom of this shell. That is about 2.5, 2.8 gigakelvin. Therefore, the main products of this zone will be, of course, products of the oxygen burning, with a small depletion of the elements produced during neon and carbon burning. But at the same time, there is also a very large production of light particles, mostly protons, but also some alphas and some neutrons. In particular, the proton captures can allow the star to produce some odd-Z elements like phosphorus, chlorine, potassium, scandium, that have been always a problem to be reproduced by classical massive star models, classical core collapse supernova models. And this is an effect that characterizes all these elements, let's say, between oxygen and the ion group elements. But there is also another impact that is a secondary impact. It depends on the initial metallicity of the star. That is the activation of photodisintegration. Since the temperature that is governing this process is the typical temperature at which the photodisintegration can be efficient, there is also a very important activation of the gamma process, nucleosynthesis, so production of the p-nuclei that are 35 isotopes of elements heavier than iron that cannot be produced by neutron capture. We'll talk about this later, but also small production of the weakest process component. I'm not going to discuss this today, but I would like to mention this. So let's focus on the first part. And more importantly, I would like you to focus on potassium, scandium, and magnesium. So this is something that I found this summer in Italy, and this is a very popular medicine to gain back energy, and this seems to be the equivalent in English version, and that's definitely catchier than the Italian version. But this is just to introduce that I'm interested in potassium, magnesium. I couldn't find any photos about scandium, but I think it's used in lamps. So let's take a 15 solar mass star as an example. This star has a carbon-oxygen shell merger. This star has solar metallicity, and this is the production factor of the elements after the core collapse supernova. By production factor, I mean the ratio between the yield of a certain element divided by the yield of the oxygen. And square bracket means that these are the logarithm of the ratios relative to solar. So basically, this tells us the zero is the same ratio of the element relative to the sun. Why the relative to oxygen? Because oxygen is mostly produced by massive stars. So if we want to compare something that is produced in a massive star site without doing some galactic chemical evolution calculation, we have to compare this with the main product of massive stars. So if this production is less than oxygen, like in the case of heavy elements, for instance, as we know, massive star cannot produce elements heavier than the first S process peak, for instance. The ratio will be less than zero and it will be subsolar. If it's 0, it's co-produced with oxygen. We can see that there is some production of the iron peak elements. They are produced during the explosion, and also, interestingly, some strontium, as I mentioned earlier. But the elements I would like you to focus on are these elements here. You can see that there is a large production of silicon, sulfur, phosphorus, argon, that are the products of the oxygen burning, and also chlorine, potassium, and scandium, that are the odd Z elements. So these are the merger, and these elements are the most produced in the ejecta. Now, I'll try to guide you and to make you understand why they are produced and where they are produced. So let's start looking at the figure on the left. This figure on the left represents two important stages of the star: before the carbon-oxygen shell merger and after the carbon-oxygen shell mergers. This is the structure, the chemical structure, as a function of the internal mass coordinate. The dashed lines are the abundances before the carbon-oxygen shell merger, and the solid lines are instead what's happening after the carbon-oxygen shell merger. And the two panels represent respectively here the major fuel of the star, so oxygen, neon, carbon, helium, silicon, and they are in a linear scale, so they can be seen better, while some other species that are important, that are products of this burning, are instead in the lower panel here in the logarithm scale. The gray shaded area, the lighter one, represents the zone that is interested by this mixing of the shells. And as you can see, after the merger, there is no distinction between the different zones that the star had before the merger. So the oxygen zone, the oxygen shell, the neon shell with a small convective neon shell, the large carbon shell, everything is erased by this mixing. And during this mixing and during this erasure, we have the depletion of carbon, neon, a little bit of oxygen, of course, because we are burning oxygen, and magnesium as well. It is the product of carbon and neon burning. But at the same time, we have a large production of silicon that is spread up to the edge of this zone that is roughly 1.5 solar masses wide. There is a large production of sulfur as well, here the violet line, together with potassium, scandium, and also the radioactive nucleus titanium that is also important for the core collapse supernova. But this is what's happening during the merger. This is the snapshot before the core collapse. Now we know that a massive star has the core collapsing and then exploding, and then the shock wave is reprocessing the material above the iron core. So what is the effect of the core collapse supernova on the merger? Well, we can see this on the right figure. The right figure basically has the same meaning as the left figure, except that now the dashed line is the pre-supernova structure and the solid line are the post-shock abundances. And the different grade zones in this case are instead the different explosive burning stages, so explosive carbon, explosive neon, and then there is the remnant mass here. The very interesting thing is that the zone that is represented by the explosion is roughly 0.2 solar masses wide, so it's definitely way smaller than the actual zone interested by the merger. And as you can see here, the abundances are not drastically changing. So the abundances of the element produced or destroyed during the merger will be those that will dominate the yield after supernova explosion and in the ejecta. But why I'm saying this, why the supernova is behaving like this? Because as I discussed earlier, the merger forms a very extended zone in radius. And since the supernova shock, the temperature of the supernova shock, especially in these layers, in the external layers, can be approximated by a radiation-dominated approach. And therefore, it scales as the inverse of the radius. So since it's crossing a zone that is very extended, is decreasing very sharply. So the impact of the explosive nucleosynthesis is almost negligible, at least for the elements that we are interested in this case. So this is This is why the ejecta of core collapse supernova with a carboxylation mergers are so important, if these stars, of course, explode, but this is another story. So this was all theoretical discussion, models, and ideas. Now, let's try to understand if it's possible to compare this with some observation, especially because it's very hard to do a full galactic chemical evolution model using carbon oxygen merger yields. So in the paper that I mentioned earlier, in the first part, we tried to demonstrate that carbon oxygen mergers can occur basically at every metallicity, at every stellar generation. If you're interested, you can ask me later, or you can read the paper. This is not the main focus of this talk, but the important thing is that if it can happen at every generation of massive stars, it can also happen at in population 3 stars, so in the very first generation after population 3 stars. So what thing that we can do is do some stellar archaeology, so compare the yields of the primordial stars with and without carbon oxidation mergers with observation of extremely metal poor stars. And this is what I did in this paper. So I collected observations from the JINA-based database, mostly of stars with a metallicity lower than -3. So we are talking about stars that have a metallicity 1000 times lower than the solar metallicity. And they are good candidates to be second generation stars, or at least very few, after very few generations. So they saw very few core collapse supernova explosions, have been enriched by very few core collapse supernova explosions. So they formed from material from the first supernovae. And these are the blue stellar symbol here in the plot. Here, the dashed line represents the average of these points. I'm considering potassium and scandium over magnesium. Why magnesium and why not oxygen? So magnesium is, as well as oxygen, produced by mostly by massive stars. The thing is that oxygen is very difficult to observe at extremely low metallicity, while magnesium is much easier to observe. So we can extend our sample in this way, even if magnesium has some problem to be fit by massive stars, but still, this can help us. And the gray shaded area here represent the classical error bar that these stars have. It is also here in the legenda, applied to the average point. So we are interested that our stellar models of population 3 stars or extremely low metallicity massive stars fall at least near this gray zone. And these are the stellar models, so the stellar yields from population 3 stars, from extremely metal poor stars, massive stars, from different set of yields. So there is no bias on the stellar code or on the initial prescription. We have Kepler models, we have Nomoto yields, we have Limoges-Kiefer. There are also my models done calculated with the Franek code as well. And as you can see here, all the models with a mass less or equal to 25 solar masses fall into this quadrant. I didn't want to include stars heavier than 25 solar masses for different reasons. First is that we don't know if these stars explode actually. It's very debated. Probably a fraction of them will explode, it will contribute. But they very likely do not experience carbon oxidation mergers. On the other hand, these stars will have, of course, higher potassium and scandium because the exploded zone will be larger, but also they will have a very large carbon shell, and this will enhance a lot the magnesium yield. So basically, all these models will sit in this part of the figure here. So they will move farther away from the points that we are interested in. So since they are not candidate for carbon oxidation mergers, I decide to remove them from this plot. So the interesting thing here is that classical models, so no rotation, Different metallicity, the highest one is -3 by Limon-Jinkiewicz, just as a reference, and different codes. None of them are able to reproduce the bulk of the data. Of course, there are two outliers here that probably can be explained with these models. But the thing is that not even mixing the yields from these models, it's possible to get into the observational area. This is because if we take two stars here, their ratio will fall between the 2 points. So this is just doing some math. If we take 1 point here, 1 point here, it will fall, the average, the double pollution yield will fall here. So it's definitely not possible using the classical models to explain this data that is dominated by roughly solar potassium over magnesium and let's say 1/3 of solar scandium over magnesium. So the thing that we need is a component here that is on the other quadrant, and mixing this component with the classical Cockcroft supernova, then we can aim to enter in the observational area. So probably you already understood what's my point here. So if we include models with carboxyl mergers, we obtain this. So the solid points are models with carboxyl merger without any restriction on rotation, metallicity, or anything else. Basically, why I'm saying this, I'm comparing solar yields with extreme metal pulsars. Are you crazy? No, because if a star has a carboxyl merger, the yields of the star, especially the scandium and potassium and magnesium yields, will be dominated by this zone, by this 1.5, 1.2 solar masses of the ejecta. And this nucleosynthesis occurring there is completely primary. It depends only on carbon, magnesium, carbon, neon, and oxygen that are in the star, that are the leftover of the helium burning. So it's not dependent on the metallicity of the star. So this is very important. We can use the nucleosynthesis of a carboxyl merger as a proxy to basically all the categories of carboxyl mergers. And this is very interesting because this is, of course, not conclusive at all, because there are some models falling here. For instance, rotating models are falling here. Push models are able to explain, for instance, scandium over magnesium. Push is a technique that allowed the star to explode with a more sophisticated neutrino-driven explosion, even if it's still 1D. And they are able to reproduce scandium more than the classical models, but they are not able to reproduce potassium, for instance. So far, at least to my knowledge, carboxyl mergers are the only possibility to populate this quadrant here. There are no other astrophysical processes that can produce supersolar potassium and scandium over magnesium. So they are very good candidates, even if they are not conclusive, to solve the problem in extremely metal pulsars for the odd Z elements. So another thing that I would like you to note is that the production of the odd Z elements in a carboxyl merger is not only related to the nucleosynthesis, but their production is also very important for the entire evolution of the shell. Of course, these are 1D models, so they have limitation, they have mixing length, so they have a lot of problems that can be partially solved by 3D models. But the thing I would like you to note is that if we compare the energy generated by the classical oxygen burning here on this side and during a carboxyl merger where there is the peak of the temperature, we can see that while in the oxygen shell the dominant process is of course oxygen burning plus some alpha captures, here the dominant reactions on the energy generation and also on the fluxes are proton captures on sulfur, phosphorus, and argon isotopes. And altogether, they can produce about 400 times more energy than the oxygen burning or carbon plus oxygen burning. So this is something that we recently submitted with Marco to Astronomy and Astrophysics, and we call this the SPARC process. Of course, this is very catchy way to remember this. So stay tuned for the results. We are still waiting for the first referee report. Okay, now in the remaining time, let me focus on the second part that is depending on the metallicity. So the second nucleosynthetic component of a carbon oxidation merger, the one that is related to photodisintegrations. So mostly I will talk about gamma process. What is the gamma process? So gamma process is a nuclear process that is able to produce these p-nuclei that are isotope of heavy elements that cannot be produced by the usual way we produce heavy elements, that are the neutron captures, because they are shielded by the stability valley. So the beta decay cannot reach the proton rich or the neutron deficient nuclei because they decay to the stability valley. So the only way to produce them is to destroy these nuclei and reach them through photodisintegration, mostly gamma N reactions, followed by gamma P and gamma alpha reaction when we reach the left part of the stability valley. So this process is thought to occur mostly in core collapse supernovae, but also in type 1a supernovae. Still not clear what is the relative contribution to this. In the past 3 years, I focused on the core collapse supernova scenario. And there are still many problems in this scenario, because even if this is one of the most studied and the most suitable production site for the p-nuclei, there are still no consensus on if stellar models are able or not to produce these p-nuclei. In particular, stellar models tend to underestimate the yields of these elements, these isotopes, and in particular, there is a very severe problem with molybdenum and ruthenium yields. So why is this related to the carbon oxygen shell merger? So as I told you earlier, and as I told you for the in the first part of the talk, carbon oxygen shell merger is regulated by the temperature of the oxygen shell. And the temperature of the oxygen shell can vary between 2.5 when the shell is developing to 2.8 gigakelvin when the merger is really working well. Because this is basically related by the fact that the core is contracting and therefore the bottom of the shell is heating up. And in this process, we have photodisintegrations, of course, because the temperature is high enough to photodisintegrate some nuclei. And this is the same picture that I showed you before, but now on the bottom panel, I put some heavy nuclei, some of the p-nuclei. As you can see, the impact of the explosion is important for strontium, that is one of the lightest p-nuclei, while it becomes more and more milder by increasing the mass of the p-nuclei, getting very almost negligible in the case of platinum, for instance. And the bulk of the yield will be again the what has been produced during the carbon oxygen shell merger. I would like to note also that while the stable p-nuclei can be mostly produced by the merger, the unstable ones that can contribute by decaying to the stable daughter can be produced also during the explosion, especially those that have a half-life of few seconds, because they can be populated by the nucleosynthesis during the shock wave, and then they decay after a certain amount of time to the parent nuclei. And as you can see here, platinum has a very important contribution from the merger, but the radiogenic contribution of mercury-190 will add a lot from this region, that is the explosive neon carbon explosive region. So this table is from our paper in 2023, and here we also studied the contribution of carbon oxygen shell merger to the production of gamma process. And here we estimated that all the p-nuclei, let's say cadmium 108, so with an atomic mass number above 110 have their major contribution from the merger. And we call this the cold gamma process because it's kept to the maximum temperature, that is the temperature of the oxygen shell, while the usual gamma process can range between, let's say, 3.5, 3.3 gigakelvin down to 2.7, 2.8, something like that. So we are cutting the lightest component, that is selenium, krypton, strontium, molybdenum, ruthenium, some palladium, that will be dominated by the explosive nucleosynthesis, because the peak production will coincide with a temperature that is higher than 2.8 gigakelvin. So the dominant contribution will come from the carboxyl shell merger for the heavy gamma process nuclei. And this is another interesting feature. So as I told you, the explosion is not really altering much the abundances of the yield produced during the carboxyl shell merger. But what if we have more energetic explosions? What if we have hypernovae? So we studied this in 2024 in the case of gamma process, but it can be also applied to the intermediate nuclei, such as OZ elements. So we took 3 different models, 15, 20, and 25 solar mass stars, and we evaluated average overproduction of these p-nuclei in terms of this F0, that is defined as the average over all the overproduction of p-nuclei, but also the F-gamma, that is a peculiar definition of this overproduction that is based only on the 3 most produced nuclei. And again, we compared with the overproduction of oxygen, because we want to estimate if core collapse supernovae are able to pollute the interstellar medium with new p-nuclei rather than destroying them. And as you can see from the 20 and 25 solar masses, we spanned 1 order of magnitude in terms of explosion energy, or if you prefer, in this case was the initial velocity of the shock. And as you can see here, for low explosion energy, there is no way we can produce p-nuclei, while we can reach the production relative to oxygen with mild explosion energy. But that's the only way we can increase our production, and we also reach a kind of saturation here. While if we go to the 15 solar mass star, that is the same star that I showed you earlier, that is the star with a carbon-oxygen shell merger, you can see that this is completely independent from the explosion energy. So even spanning 1 order of magnitude of explosion energy, the total yield ejected in terms of gamma process nuclei, p-nuclei, it's not really changing. And also the nuclei that contribute to the F-gamma, there are the 3 most produced p-nuclei, do not change at all. So the dominant contribution will come from the carboxyl shell merger and not from the supernova explosion. So this is my summary conclusion. I really hope that I convinced you that carboxyl shell mergers are definitely a phenomenon that is worth to investigate more, and especially from 1D and from 3D point of view. And they can really contribute to the enrichment of the galaxy. To some extent, we try to estimate that doing some stellar archaeology, but full GC work is needed in this sense. Also, then we have some open question still. So what is the frequency of this carboxyl shell merger? So what is the origin? What is causing eventually the merger of this thing? And is there a trend with initial mass? So I told you that masses lower than 25 tend not to have carboxyl shell mergers. And of course, we know that there is a threshold limit on the initial mass for the successful supernova explosion. So between electron capture and core collapse supernova. So are the lower massive stars able to do carboxyl shell mergers as well? And is rotation helping this? We partially explored this in the previous paper. And also, what is the role of nuclear physics? There are a lot of uncertainties, like convection, for instance. Also, mass loss can alter the size of the core and eventually change the occurrence or not of carbon oxidation merger. But what is the role of nuclear physics? Can we rely on oxygen fusion? Can we reduce the simulation to a few number of isotopes to simulate a carbon oxidation merger? So these are all open questions. I hope I interested you enough in this topic, and I'm looking forward for your question.